Okay, so it's my great pleasure to welcome everybody to today's Spring 2021 Nonlinear Analysis Seminar Series. Today's speaker is somebody who I've known for a long time, since before we were both doctors, back in Carnegie Mellon, and you were at Oxford at the time, is that right? So Philip Rindler, and has been a friend for a long time, so I'm very pleased to welcome him today. And today, Philip will be speaking about shape optimization of light structures and the vanishing mass conjecture. So welcome.
Okay, so thank you very much for the invitation. I hear it is hang on, let me just share my screen. I hear it is the cherry blossom time, I think, in Japan right now, right? It's certainly cherry blossoming here, so I assume this is a worldwide thing. So thank you very much. Of course, I would have loved to see that in person, but hopefully I get the chance to come in person sometime in the not too distant future. I think it was planned, Daniel planned to get me over there in person, but I think then because of the pandemic, it never quite materialized. So in any case, so thank you very much for the invitation. So today, I'm going to talk about some very recent work, which is joined with Jean-François Barbajan and Flaviana Iolano, who are both based in Paris. And it was finished during the pandemic, but started before the pandemic. And it's about optimal light structures and the vanishing mass conjecture. So I will explain quite a lot about the problem itself, actually, and it will take a while until you see our theorem, because I felt it would be useful to give you a fairly a little bit more of an introduction to the topic, because I don't think it's been as prominent in analysis recently. Right. So when I say shape optimization, what do I mean? So it's a fairly common process in engineering. You start with a design for some piece. So let's say this is some sort of joint between two pieces, and then you analyze this with finite elements as you would. And then you realize that you see here, there's some sort of points which have high stress. And if you do this a lot, in reality, this thing might break, and it will usually break around here. I mean, the prediction is not always accurate, but you want to avoid very high stresses, because that's where the material will get tired and eventually break. And so then what you can do nowadays is you can do optimization on the shape. Yeah, and you can run this with some code, and you might get something like this, which looks a bit more like an alien hand. Yeah, so this is what some sort of topology optimizer or shape optimizer would spit out. Okay, it's not very practical to manufacture something like this. So what then people do is they kind of build a design based on what this topology optimizer gave, and then hopefully analyze it, and it will be better. And I mean, better, what does it mean? So it could be stronger, or it could use less material, or be more resilient to structural failure, things like that. So this is a very important thing, and it's done effectively every day for people who do real manufacturing. But on a theoretical level, quite a few things are not known, and it's an interesting problem, I think, to understand, and perhaps it's not been as active in our community to look at this problem. It's been more of a numerical problem recently, but I think there's some real interesting analysis problems connected to this that are open, and one of them I want to tell you about today. So let me start the mathematical journey, if you want, by telling you a little bit about the modeling of this problem and mathematizing it and modeling it. Okay, so so we are in really the standard setup of linear elasticity here. So we are either in 2D or 3D, and we have a specimen. So this is our body, and it's some open subset of Rn, and bounded, and it has a nice boundary. Yeah, I mean, maybe smooth, maybe C2, maybe Lipschitz, so on. And then you measure the deformation by the displacement. So that's the change in position, right? So if you have your body omega here, there's a deformation, this thing gets deformed, use the displacement telling you where does a point here get mapped to this. And because it's the displacement, so the difference between points, the shape that you see is the identity plus u of the original shape, okay? And of course, we want to understand what's the energy of such a deformation of the body. I mean, if you think of this as being rubber, you know, squeezing it or pulling it or stretching it, you want to measure the energy. And that's usually done in a functional like this. So you have a quadratic term, so which depends on the linearized strain. So that's the gradient plus the gradient transposed over 2. That's somehow a delinearized measure of deformation, this linearized strain. And then you plug this into a positive quadratic form, which models the material response. If you want to not think too much about what this fourth order tensor C is, then just think of this as being something like the norm, the J of psi could just be 1/2 mod psi squared, just a Frobenius normal. So, and this is actually the case we will be looking at because it's difficult enough. And then you have a boundary force, which is like the force you push on from the boundary. So let's say you're squeezing it from one side, and we'll just give that this is an L2 function, but on the boundary, okay? And then the energy given is this functional, and of course it depends on u, and it depends on the domain omega. And I'm highlighting the domain here because we will later want to vary that domain, right? Because we're trying to optimize shapes. And now there's one thing which is slightly different here from a lot of the classical modeling. It's really not a difficult point, but it's more of a technical point. And I want to say that, so what do we select u from, right? What space do we look for u? And as usual, we look for H1, so Sobolev spaces with one weak derivative in L2, but we mod out the rigid body motion. So these are the skew affine maps. So X goes to Sx plus B, and S is a skew symmetric matrix, and B is just a position. This isn't really anything, there's nothing deep about this and nothing necessary about this. It's just basically to fix one framework. This corresponds to that you can kind of shift the body in space. So the body isn't fixed at one point. Basically the same thing I'm going to do, you could also do for if you fix boundary conditions, but there's some additional technicalities that I don't want to get into. So I'm just fixing this for the simplest possible framework that's interesting and non-trivial. And then it's fairly easy to see that if you look for u modded out in R, of course, you know, the symmetric gradient of R, or u can change. If I change u by a function in R, then, well, the gradient of u will change. But the point is that the symmetric gradient, so the linearized strain, will not see these shifts, right? Because these are skew symmetric matrices, so they're not seen by the symmetric part of the gradient. And to make this all kind of well posed, you need to ensure that the exterior force satisfies some balance condition. As I say, you won't see this again. It's basically just to make the problem well posed in a simple case. You can think of more complicated situations, but it actually doesn't change the real problem here. And okay, so before I go on, let me just say one point, namely that, so this is really a linearized framework, okay? So we're not looking nonlinear elasticity here, and this is already complicated enough. Okay, so now I said I want to optimize the shape, right? I mean, it's shape optimization. And so I'm picking myself a set called A epsilon, and these will be all the admissible shapes in which I can arrange my material to create a shape which has certainly some desirable properties. And so I want to prescribe the size. So if you want, I give you only an epsilon of mass, okay? And then I'm looking for domains. These are Lipschitz domains. They're subsets of omega, of my big surrounding domains. And I need some technical condition, which basically means that I have to, if my omega is here, I have to, so this is the boundary of the big omega, and this is the boundary of the small omega, but the point is that the small omega covers all of the boundary. Again, this is just a technical thing, because if I don't do this, my boundary force might not be, I mean, I'm saying I have a force somewhere on the boundary of big omega. And obviously, if my small omega doesn't touch that, I cannot kind of react to that force. So there will be no solution that accommodates this force. It's really just a technical thing. Again, if you don't, if you want, you can ignore this. But really, the important bit here is this, namely that the size of the domain is epsilon. Yeah. Oops. Sorry about that. I don't know what happened here. All right. And so what do we want to optimize? Well, we want to optimize what's called the stiffness. The stiffness is basically how strong the material is, or how much it resists deformation. And this is defined as the minimum of the energy for a given shape. And this makes intuitive sense, right? Think of it this way: U will be optimized over all deformations. And then I pick, I mean, the higher the minimum energy is, the stiffer the thing is, because the minimum energy is kind of the energy I cannot get rid of by deforming the thing, yeah? So you have your body, you adjust it to its energetically optimal shape. And whatever energy remains in the body, I cannot get rid of by deforming it. So the more energy remains in the body, the stiffer the thing is. Again, so this is a well-established quantity in mechanics. So, but let me say this, what it means. And of course, here I've just plugged in the definition, right? The point is that here now I'm integrating over small omega, and here I should also be integrating over small omega, but F is supported on the boundary of the big omega. And so this integral stays the same. And here you see why I need this condition. If I didn't have this, somehow this term would be kind of ill-defined, because I might not have material where this force attaches. Okay, so now if you know a little bit about the calculus variations, you would like to show that, I mean, I wrote that there is a minimum. How do you know there's a minimum? It's not just an infimum. Well, this problem is very standard in the calculus of variations. It's I mean, this is a convex, it's a quadratic form with a linear force. I mean, this is as standard as it gets. The only little issue is that you're doing it over the symmetric gradient and not the classical gradient. But we have so-called Korn's inequality, which tells you that at least in L2 or in H1, in this particular space, because I've modded out the rigid deformations, I have a nice inequality which tells me that this linearized strain actually controls the gradient. This is in some way not optimal. Actually, Daniel is an expert for better estimates of this form, but we'll only need the standard one here. So one thing I would like to say, though, is that this constant here is very much dependent on what omega is. Yeah, in fact, there's some results by Levica and Müller, which give you very precise information on this, at least in 2D, but it's the same in 3D, that if you have a very thin shell, so you have like a domain that looks like this, and it has thickness epsilon, as epsilon goes to 0, this Korn constant blows up to infinity. So, and you can already see if you're trying to optimize shapes here, we have an immediate problem, right? Because, I mean, effectively, the fact that if we want to let epsilon go to 0 or something, the constants in the problem will blow up, okay? So you have a problem, because somehow finding a good U depends on having some sort of constant. And if it's not uniform in epsilon, you run into trouble. So this is something to keep in mind. Okay, so now I can actually tell you what, if you want, the goal of shape optimization is, at least in the classical or the most prevalent framework. And it is to maybe I start at the bottom here. So given a bounded domain omega, find the optimal shape, small omega, of prescribed volume, and maybe with some technical condition, that is maximally strong. And so that means it's the maximum over S of omega. So the stiffness is maximal. And because by historical precedent, I prefer minimization problems, I just switch a sign here, and I want to minimize the C epsilon, and that's called the compliance. And for some reason, to make this not decay to 0 in epsilon, I multiply it with epsilon to not not blow up, okay? You will see in a minute where this comes from. But so I want to minimize the compliance. The compliance is minus the stiffness. So this is my problem. And I'm doing this over all the shapes in my admissible set, okay? And so when I say, maybe I briefly touched on this at the beginning, there's really 3 types of shape optimization. So the first is what's called size optimization. So I give you the structure, and the only thing I can do is like I change how thick I make those beams, okay? And if you do this, for instance, for a bridge, you will get effectively that these beams will decay to 0 with thickness 0, and these ones will become somehow strong to sustain the forces. But I've given you the structure. And the second thing is so-called shape optimization. There's a bit of a ambiguity in the term here, where I give you the topology, but I can change the shape. Yeah, so I've give you, I don't know, 6 holes, and you can kind of deform them in some way, but you cannot change the fact that you have 6 holes. And then the final, which is the version that we're interested in, is so-called topology optimization, where I just give you some sort of block of material, and then the algorithm you're trying to optimize also over the topology. And of course, this is more problematic because now it's not even clear how do you even describe things like that. I think it's fair to say that in terms of numerics, the shape optimization like this is probably more common than this full topology optimization. But because nowadays we can actually 3D print quite a lot of things, and this additive manufacturing has really changed the amount of shapes we can create in reality, topology optimization and those more advanced things become more and more important. Okay, and so what are light structures? Well, light structures are what happens in the vanishing mass limit, where epsilon goes to 0, okay? And I want to maybe make the point that this is not just a mathematical problem, because what you see in practice is, of course, that epsilon is small. I mean, the amount of shape you're printing relative to your big ambient space is always less. I mean, it's always only a little bit. So if you have a 3D printer, right, most of it is void, and then you have a little bit of stuff that gets added up. And so really, this question of what happens in the limit is a question of what's the effective problem for small epsilon, right? So what happens in the limit, and that's a hard problem, as I want to explain that in some more detail. But before I do this, let me give you a little bit of a history of the problem, because I think it's quite interesting. So this started really in 1904 with Michel, who looked at this just from an engineering point of view and tried to find structures like bent beams, if you want. This was all 2D, which somehow try to accommodate certain forces. So I think here's a force pulling down or pushing down, and you're trying to find an optimal structure kind of accommodating this force, but only made out of beams. Because beams, if you want, they are lower dimensional, so they have no mass, right? So it's a question of what is, I mean, a beam seen as a measure is supported on a lower dimensional set, or maybe it's very thin relative to everything else. And okay, so he had these curved beams, which are kind of hard to do because in practice you can't really manufacture them. So then Praga in the 1970s kind of thought about the same problem, but now having straight beams and just kind of seeing this in the limit of the number of beams going to infinity. And then I think the mathematical theory started in the 80s with very influential papers by Cohn and Strang, and then by Alea Cohn in the 90s. And they looked at it, if you want, on a pointwise system, in a pointwise way. But I think for this work is quite important is this work by Bouchité in 2001, and it was really only published in a conference proceeding. Now he's put it on the archive, I think last year or so that people can actually read it. And so he formulated a general conjecture of what you should be able to see in the limit as epsilon goes to 0. And then he also published this paper by Bouchité and Butazzo, where they showed some very interesting connection, which I will come back to a bit later. And then in 2002, there was this book by Allaire, which is very influential. So you can see in 2001, a lot of stuff was happening. And I think there was some sort of transmission of brainwaves, because so I was still in high school and we were given the task of building bridges with lower dimensional structures, which I found this old picture of what I did in 2001. So this is balsa wood, right? And you're trying to, you were given a limited amount of balsa wood and you're trying to build the strongest bridge. So Felton, she has done much better than me. She runs a chocolate cafe now. So there you go. And so we did this group work, and I can reveal that our bridge was not the best. So I think it's best for me to work on the theoretical side of the problem, not try to actually construct things like this. Yeah, and then there has been a lot of work on this. I mean, there's a lot of people who've worked on this over the last couple of decades. So I want to mention Bonnetier, Bouchité, Fragala, Frankfurt, Gangbo, Jouve, Olbermann, and Sepesha. So there's a big body of work on it. But all those results, they don't enforce the mass constraint strictly. They basically take an additional penalization term in the mass and then work with some sort of Lagrange multiplier theory. So, and in fact, what we do is consider the problem where the amount of mass is given, fixed epsilon, and that will be it's a bit different. Right, so, but before I continue on showing you our theorem, we first need to actually get this problem of shape optimization into a form that we can actually look at in a more fruitful mathematical way. I mean, you've seen there was this problem with the Korn constant blowing up, and there's a lot of other issues here. I mean, for instance, when epsilon actually goes to 0, what is some sort of shape? Yeah, it's not clear what a shape is. And in fact, it's well known that you cannot define displacements of generalized shapes in that sense. So there's some sort of mathematical problems, and they are solved by dualizing the problem. So let me briefly recall that if you have a function j of x, j of xi, you can define its convex conjugate. And that's the supremum over xi colon tau. So this is the Frobenius product of these matrices, symmetric matrices, minus j, and then you optimize the xi. And geometrically, you can think of this as being the intersection of the highest supporting hyperplane of the graph with the y-axis, and then flipping the sign. Okay, so this is your f, this would be your j. You look at the highest supporting hyperplane, you look at the intersection with the y-axis, and the supporting hyperplane with normal x star, and then the intersection is minus f star of x star. So this is, if you want, a graphical way of understanding this conjugation. The point is that convex conjugation allows you to do some sort of switching of minimum and maximum. So there's a min-max duality here. So this was our stiffness. Remember, it was the minimum over E of U omega over all of those U from this space. And now I'm plugging the definition of the energy. And this min-max theorem, which is very classical convex analysis, tells you that this minimum is equal to the maximum of minus J star. So here's the dualization. I'm going from J to J star. And now I'm not taking this over, I'm taking this over all sigma, which are called statically admissible stresses. So this is the classical mechanics. If you dualize, you go from displacements to stresses. And these are L2 functions which satisfy this differential constraint. The divergence of sigma times the characteristic function of your set omega equal to F. And F supported on the boundary. That's my force. This is really kind of classical. You can look this up in Ekeland-Temam. And so you can rewrite the stiffness now as a maximum over something else. And so recall, so this was where we ended up on the previous slide. And now I want to find some sort of measure theoretic formulation of this. And the reason I want a measure theoretic formulation is because the sets omega, if I let epsilon go to 0, they have size epsilon. So what do I have in the limit? Well, they have to concentrate in a null set. But of course, a null set is very hard to describe. And in fact, you could have some sort of diffuse structures. And then you don't really know what to do. So let's reformulate this in a measure theoretic version. And then with the measure theoretic version, we can actually explain more what we want in the limit. So remember, the compliance was defined as this minus epsilon times the stiffness. Okay, so let's pull this through in our formulation. I should say what I have done here is because again, I like minimization problems better than maximization problems. I push this minimization, this minus sign inside, I get a minimum and it cancels with this minus sign. I've got my epsilon here, and this is what I end up with. And now what I just do is I replace chi omega dx by the measure mu omega, which is a probability measure. It's the Lebesgue measure restricted to this set omega divided by epsilon. And if I do this, obviously, if I do this, here I have 1 over epsilon somehow. So I get a 1 over epsilon, but here the epsilon inside of J star, because it's quadratic, cancels both this epsilon and that epsilon. So this is the correct formula. And here I plug in again, epsilon times mu omega is chi omega. So I have rewritten this. And now what I just do is I replace epsilon sigma by sigma. I've just absorbed the epsilon in there. And I write that sigma is now an L2 function with respect to mu omega. Okay, so this is really just a very elementary manipulation. But the point is, now I've written my compliance really as a functional of a measure. So I can write C epsilon, so the curly C epsilon of mu of any measure, but it's C epsilon of omega if mu has this particular form, and it's plus infinity otherwise. Okay, so now I can define, I have a compliance functional or generalized compliance functional defined for all probability measures. And now I can ask what happens in the limit as epsilon goes to 0, because now I can actually make sense of probability measures on a compact domain passing to the limit are still probability measures. So it kind of makes more sense what the limit object should be. So, and let me just remark, there is a nice coercivity here that if the C epsilon of mu epsilon are uniformly bounded, I can actually get a uniform bound on the mu epsilon. In fact, I mean, the mu epsilon are probability measures here. So this is if you want a triviality. And then I can select a subsequence such that the mu epsilon converge weakly star to some limit measure. And this limit measure, I want to consider a generalized shape, okay? Because that is somehow a representation of what happens in the limit. And let me give you one example that shows you that something funny can happen, or I mean, something more happens than just a null set, which we would not see in integrals. So let's say our shape or our structure looks like this. So it's some sort of beams, horizontal and vertical, okay? And then I refine my shape. So I have, again, these beams, but now with higher frequency. And then I do this again, I refine and refine. And of course, as a set, maybe if I make them very thin, this might converge to 0. I mean, maybe this isn't so visible here, but if I want to make these holes big, I can arrange the rescaling so that actually in terms of the size of the set goes to 0. But of course, in terms of the probability measure, which is multiplied by 1 over epsilon, this might converge to a density. And it's in fact a homogeneous density here. So it's just whatever, something times Lebesgue measure on the domain. And this has a real meaning in the problem. It means that it represents a shape which is a fine oscillation between horizontal and vertical beams. And while the limit shape cannot tell you precisely how they are arranged, it tells you that somehow they're doing this with a certain, I mean, density. And that's kind of, so when you manufacture a shape like this, what would you do? Well, the instruction would be manufacture this as finely as your machine can do, and you'll be as close to the shape as you can be. So the cutoff of the precision of your machine is that. But of course, in the mathematical terms, you want to be you want to see it as a density of horizontal and vertical shapes, beams, and that so it's a well-defined mathematical problem, and it really has physical meaning. Yeah, I mean, these shapes here, they have, if you want, microstructure. That's why people do with young measures as well. Of course, in a real crystal, there is no such thing as infinitely fine microstructure. But of course, from a mathematical point, if you disregard atomistic effects, it's very sensible to say, well, you're oscillating as quickly as you can between, let's say, two phases. And this is kind of the same thing here. And so now the real mathematical problem is, okay, you have these C epsilon, you minimize those, so the compliance over your admissible shapes, and you want to know, what does this converge to in a variational sense in the limit? So what is a limit compliance C bar defined on probability measures? And so you don't just want that the minima or the infima converge, but you also want some sort of property saying, if you have approximate minimizers of the C epsilon, please, they should converge weakly star to a minimizer of the limit functional C bar. And also, if you have a minimizer of the limit functional, that should originate from a sequence of approximate minimizers of the C epsilon. Okay, so this is if you want a mathematical formulation of our problem. I see there's a question.
Yeah, if I quickly could. So that's I like the presentation to this homogenization result, but something perhaps is the microstructure. So when you think of, you've got a limit measure which is homogeneous like this, you still have to make the decision if you were to infer on a fine structure about the actual pattern. So how does one try and capture that information? Here you've got a fourfold symmetric structure, but how would you infer a sort of a next order?
Yes, so that's a very good question, and it's exactly the question that underpins this work, because, so of course, I want to get to the point where I identify the C bar. And the C bar will have, maybe I'm not stealing any thunder by saying that the C bar will have a different integrand. And if you look at the pointwise minimizers of the integrand, you get the locally optimal structure that you should be using for a certain density. So I will have an example in just a moment where you can kind of construct an optimal structure. So the result that we have by identifying the limit integrand tells you precisely what the optimal lower dimensional structure is you need to layer in order to actually do the optimal thing and lower the energy as much as possible. So it will come. Yes, I completely agree. It's a perfect question, and this is exactly what is, if you want the application of this work. And effectively, this is the next slide. So let me give you an example just to show you what one can do here. So we really are working with the simplest possible integrand, which is just isotropic and homogeneous. So it's 1/2 the Frobenius norm squared. And we take mu to be L2, so the Lebesgue measure on the ball in 2D. And sigma, now sigma is this kind of optimal stress, or it is some sort of stress in the limit. Let's assume I see a particular stress, and it's given us just a diagonal matrix, alpha 1, alpha 2, with the property that these alphas are ordered as singular values. So it's a symmetric matrix. So the modulus of alpha 1 is less than or equal to the modulus of alpha 2. And I want to show you what the optimal structure is, and then you will see something interesting. Okay, so this is the optimal structure. You've already seen it. It's some sort of beams in this direction. And so it's horizontal beams and vertical beams. And let me show you what I mean by this construction. So you take a parameter gamma, which is just between 0 and 1, and you set omega epsilon, which is the shape I claim to be almost optimal, is D1, which are the vertical beams, plus and D2, which are these horizontal beams. Note, I mean, they do intersect, but okay. And this little annulus. The annulus I just need to satisfy this funny requirement that I cover the boundary of the large omega. And now I set sigma epsilon roughly to be alpha 1 over 1 minus gamma in the first component, and alpha 2 over gamma it's alpha 1 over 1 minus gamma on the horizontal beams and alpha 2 over gamma on the vertical beams. And then mu omega epsilon is just if I arrange this correctly with epsilon, then this has exactly size epsilon. roughly size epsilon if you want, and I need to adjust a little bit, but only by some sort of perturbation. And this is somehow my Lebesgue measure on those beams, and this converges weakly star as epsilon goes to 0 to the uniform measure, right? It's just finer and finer horizontal and vertical beams. And now you can check easily that the divergence of this thing is 0. Why? Well, because, I mean, the first component here, D2 epsilon, these are the horizontal beams. So this function only changes in x2. So that means if I take the first derivative of this, it's 0, and here's a 0 anyway. So this is row-wise divergence free. And now, okay, you make a short computation. What is C epsilon? So my compliance for this structure, okay, it comes out as this formula. So it's 1/2 of alpha1 squared over 1 minus gamma plus alpha2 squared over gamma. Okay, and now I optimize gamma. So gamma is the relationship of how thick do I make the horizontal and the vertical beams. And you can obviously, we can all do this just about, and you get some optimal gamma. And now the funny bit is, if you plug this in to my functional, I get that the limit compliance is this thing here. So the compliance is alpha1 plus alpha2 squared. But okay, that's some function. But the weird thing is, if the limit compliance was also had the same integrand, J star, which is what we started with J star, so it's convex and quadratic, so obviously the relaxation is the same functional. Well, not here. So you would get this functional, and you can easily check that this is larger than this one. So what's happened here is that by arranging things in some sort of complicated way, I can actually not go down all the way to J star. So actually the relaxation, if you want, what is the energy contained in a homogeneous measure? This is the optimal microstructure. This is the optimal layering of this. And it's higher than what you would get by just going to J star. And the point I want to mention here, why is this? The point is that this divergence constraint interferes with you doing whatever you want. I mean, you have to do something that's divergence free. So somehow the divergence PDE constraint interferes with the relaxation. So you only get something that's optimal along divergence-free sequences and not along, I mean, that's a restriction, a real restriction, and it plays in the relaxation. So you cannot just forget about it. Okay, so now what is Bouchitier's conjecture in this paper, which I tried to solve practically in 2001. So he claims that the limit compliance is given as the following. It's C bar of mu is the minimum over all of those sigma satisfying this constraint, this divergence constraint, with a new integrand J bar star. So what's J bar star? Well, it's the convex conjugate of J bar. What's J bar? J bar is the convex conjugate of J star, except here comes the real kicker, that the determinant over which I test is 0. So you only do this, it's like a partial conjugate. You take the conjugate of J star, but you test only with singular matrices. This is kind of funny because, I mean, this I had never seen before. But of course, if you know what I have been working on before, this is not totally, this immediately tells you something's going on, because there is something that Tata studied associated to every differential operator, and it's called the wave cone. And what you do is you take the Fourier symbol of the constraint, which is the divergence, you look at the kernel of the Fourier symbol at lambda, and then you take the union of all of those kernels. And if you do this for the divergence, this is well known, you get that this is exactly the singular matrices. And somehow you see there's a connection. And it makes sense because we have a divergence constraint, right? So there's some sort of clear connection. But it's a kind of an interesting thing because I certainly hadn't seen kind of a partial convex conjugate before I read Bouchitier's paper. And so now I can state our theorem, which has been on the archive for, I guess, something like 2 months now. So you have a C2 domain, and we prove Bouchitier's vanishing mass conjecture, at least for the simplest of integrants. which is complicated enough. So we have that the infimum over these things converges to the infimum of the limit compliance, which is given by this precise J bar star as Bouchetier conjecture. And we have these variational properties that minimizers of C epsilon converge weakly star to a minimizer of C bar, and minimizers of C bar originate from approximate minimizers of C epsilon. Okay, so we really have kind of the variational, you can really call C bar the variational limit of the C epsilon. It's not quite gamma convergence because we can't construct a recovery sequence away from the minimizer, which is kind of interesting. There is basically the reason is that these Korn constants blow up, but we can do it for the minimizer. And so as a corollary, you can understand this as a justification of the Michel-Truss theory of 1904 for the first time in a rigorous framework. Okay, so we can actually show that effectively what Michel proposed, namely that you can always find some sort of optimal way of arranging these trusses, is actually true, at least in, once you've formulated the problem correctly in a mathematical sense. So this is if you want a full justification of this. Okay, so before I go to something, let me make a comment, which I think is perhaps not so consequential that it's not needed, but it's kind of illuminating, hopefully. So remember, we have this differential constraint that the divergence of sigma mu is equal to F, restricted as so a measure on the boundary. And in fact, if mu has a singular part, it follows from a theorem that I proved a few years ago with Guido de Filippis, that these matrices sigma actually are singular everywhere on the singular part. So basically what we prove is that they have to lie in the wave cone, and the wave cone, as we saw, were the singular matrices. So there is a nice lemma of Bouchetier already in this paper, where he proves that J bar star is actually the same thing as J star if the determinant of tau is 0. So on singular matrices, there is no difference in the new integrand. Okay, so if mu, the limit measure, was purely singular, well, then C bar is actually where you started with, so nothing has changed. So in that sense, there is no new integrand. The new integrand only comes to play if mu, so the limit measure, has a diffuse concentration as the one we saw. Yeah, we have this oscillation of horizontal and vertical beams giving a homogeneous measure in the limit. And this is really false for diffuse concentrations, okay? So they really differ. And so the point is the diffuse concentrations are where all the action happens. This is to some degree not totally surprising, but what I want to say is that understanding these kind of sequences of concentrating measures has been a kind of a pivotal theme of my research over the last couple of years. So I think this fits in quite well, but it's a slightly different angle here. Yeah. Okay, so I guess how much time do I actually have left? What is the cutoff point here when my video gets turned off?
I mean, this is the online seminar, so people can leave when they want, but you go as long. So yeah, if you want to go for another 15 minutes, even is okay.
Yeah, perfect. Yeah, that's perfect. That's perfect. So I want to just show a few ideas of the proof. Basically, I want to it's not so much that I want to give you complete arguments. I want to give you just some sort of ideas. Particularly for the upper bound, I think I'm just going to try to explain why there's an interesting bit rather than how you actually do it in the end, because it's a bit technical. But the lower bound is actually fairly straightforward. I mean, it's not so straightforward to find, but once you have the right lemma, it is fairly straightforward. So what do we need to show? We want to show that we have these measures, right? Any measures, and they converge weakly star to some mu in the space of probability measures. And we have, these mu epsilon are really the measures associated to shapes omega epsilon. And I want to show that C bar of mu is less than or equal to the lim inf of those C epsilon. And then somehow the other thing I need to establish is that C bar is also greater or equal than the lim sup of those things. Okay, so then we know that C bar is really the limit of those. So it's the classical gamma convergence argument that you have a lower bound and an upper bound. So let's do the lower bound first. And so what we will use, and this is really, if you want this our proof hinges on this kind of elementary lemma, but somehow which, and let me explain it to a little, to some detail. So I give me a psi, which is a symmetric matrix, and it has the property that the eigenvalues of psi, the squares of the eigenvalues, sum to something less than or equal to 1. Okay, so that's the set. And now define q psi of tau being, okay, 1/2 tau squared, so that's our integrand, minus psi colon tau, which is the Frobenius product squared. Okay, whatever this is some sort of function. And what we prove is that this is lambda diff convex, so it's convex in directions of singular matrices, and this means that it's quasi-convex for people who know that terminology. This is because it's a quadratic form. And okay, so this is somehow you can prove this. I will say in a minute what quasi-convexity means, but I want to just state this here for people who know what this means. It's a certain convexity property. And not only that, but in fact, J bar star is the supremum over these 1/2. So this is my J star tau minus q psi if I optimize over all of those q psi. Okay, so kind of if I pointwise do this and I get the best one, I will actually recover J bar star, which is kind of an approximation property of J bar star. And I do so with diff quasi-convex quadratic forms. That's the key here. And so this is not totally out of the blue. So actually already in the 80s, or maybe even the 70s, I don't actually know when this example came up, Luc Tartare proved that a certain funny quadratic form, namely this one down here, is lambda diff or diff quasi-convex. And in some way, you can see this one here as a generalization of this, right? If you take psi to be the identity, then you get the trace here. Okay, maybe there's some factors slightly different, but it's effectively the same thing, yeah? And so this is really a generalization of this Tartare example, but it has this great property that you can write J bar star as the supremum of all of those. And once you have this, the proof of the lower bound is fairly straightforward. So actually, I should say, before I go on, this proof here is basically just some collection. It's just linear algebra, but it's a bit tricky. It's not hard, but it's also somehow you have to play around with it a little bit. Okay, so now let's take our sequence of measures with these shapes, and let's say it converges to mu epsilon. Mu epsilon converges weakly star to mu, and then it turns out that the tau, you can define a tau epsilon. That's just defined as square root of epsilon, sigma epsilon, mu epsilon, and you can show that this converges weakly to 0 in L2, but now it's L2 with Lebesgue measure, and the divergence converges to 0 strongly in H-1. Don't worry, this you can just show. It's just kind of messing around with the definition. It's not hard. It's just kind of writing it out. Okay, but the point is that now you do have convergence here in spaces which don't depend on the measure mu epsilon. It's just normal L2 and H-1. Okay, so now how is our proof? Okay, so we look at the lim inf of the C epsilon. Well, choose the sigma epsilon to be almost minimizing. Okay, then the lim inf of this C epsilon is just lim inf of 1/2 sigma epsilon squared d mu epsilon. That's just a property that the sigma epsilon are almost minimizing. Remember, it's a minimization over the stresses. Okay, so now I do the nice thing. I subtract q psi for some fixed psi, and I add q psi and pull the terms apart. We can do this for lim inf, right? The subadditivity of lim inf, superadditivity. And the nice thing is this term here. Here I have a diff quasi-convex form, quadratic. This is diff quasi-convex. Tau epsilon converges weakly to 0, and the divergence converges strongly to 0 in H-1. And then we can use Tartare's theorem on compensated compactness, which tells you that this thing is greater or equal to 0 in the limit, has a sign in the limit. So this guy goes away, right? So what happens, what remains is this guy, this tau epsilon. Maybe I was too fast. I should have said what I have done implicitly here is I've rewritten this expression with tau epsilon. Just take it on trust that this is the same thing. Okay, there's just some square root of epsilon smuggled in and divided out again. Okay, so now I'm here. So this one here, remember q psi, sorry, let's go back. Q psi has this particular form here. So if I take q psi minus this bit here, or this bit minus this, what remains is this bit. So now I end up with this here. But this, I can now rewrite back for sigma epsilon mu epsilon. And it's fairly easy now to see that under the convergences, which we assume, this can be, this is now really quadratic. This is just a quadratic form. So you can really take convex, you can use some convex results that this in the limit will be bounded from below by the limit of those sigma and mu. Okay, again, this is fairly straightforward to see once you know what you're doing. But now the great thing is I can optimize psi locally, right? So let's say this works. So I'm allowed to choose psi dependent on the point x here, which is a bit of a technical argument, but it's not that hard. And then here, this guy actually goes to j bar star. And that's what I want to show, because now at j bar star over sigma, this is the infimum over all such sigma. So I have shown my, if I look at this, I have shown my lower bound, okay? And so it only hinged on having this very nice family of diff quasi-convex quadratic forms, which have this approximation property, right? That's kind of the key here. And this is kind of reminiscent of a previous paper I did with the same authors, with this Flaviana and Jean-Francois, where we did this in a different context. That's how we got the idea of applying it to this problem. Okay, so this is how you can do this. And this can be made rigorous, this local optimization, okay? It needs a bit more technicalities, but that's basically the idea. Right, and that proves the theorem at the lower bound. Now for the upper bound, I want to just say a few words. And actually, I don't want to really tell you how we do it. I want to focus a bit on the connection between the hard constraint, where you fix the epsilon size of your shape, and the soft constraint, where you have a penalization term. So the function of the soft constraint looks like this. So you have your integrand, and now you penalize the size of omega epsilon, okay? So if omega epsilon has size 1, if omega epsilon, if this is uniformly bounded, you get that the size of omega epsilon has to be bounded by a constant times epsilon, right? So this is a soft mass constraint enforcing that omega epsilon is roughly of the size epsilon, okay? So of course not the same thing, but somehow this is all the previous results that existed in this space use this formulation, okay? There was nothing before what we did on the hard constraint. And okay, so one way of doing this, you can actually rewrite this for yet another measure lambda, which is sigma epsilon mu epsilon. You pull those two together, and then you can convince yourself that this integrand can be written as epsilon over 2 times lambda epsilon squared plus 1 over epsilon chi omega epsilon. And this integrand I call h epsilon of lambda epsilon. Now, people who know this area will immediately recognize this integrand. That is the Cohn-Strang integrand. The Cohn-Strang integrand is precisely epsilon over 2 tau squared plus 1 over 2 epsilon. Or it's possible I forgot an epsilon, a 2 epsilon. I think there should be a, maybe we make a 2 here so that, but obviously makes no difference. If tau is not equal to 0, and it's 0 if tau is equal to 0. So here's a plot. So it looks like this nice parabola, and then you have the point at 0 down here. And then for epsilon being smaller, you shift up the parabola and make it flatter, but the point at 0 remains where it is, okay? This is obviously kind of a slightly strange integrand, and in particular, it's not continuous. So it's some things that you are used to using are not true. And in fact, this integrand only has linear growth that is uniform in epsilon. So think of this, it's just Young's inequality. If you take tau, the modulus of tau times 1, and you apply Young's inequality, you get precisely this thing here, So this integrand bounds only the modulus of tau. So if you want, you are in the linear growth functional setting here, at least with regards to lambda. So now maybe I should tell you what the diff quasi-convexification of this H epsilon, how is it defined? Well, it's the infimum over all of those integrals over the unit square, and you test H epsilon with all phi, which are periodic on the unit square, have average tau and divergence 0. And if you take this infimum, you get some sort of some other function, which is called the diff quasi-convexification. So that's like the correct version of convexity when looking at sequences which have a divergence constraint. And the great thing is that this has been computed. It's a mess to do this for more complicated integrands, which are not looking like the Kohn-Strang integrand. But here you can do it, and it gives you some formula. And in this formula, whatever it is, some funny thing appears, rho polar of tau, which is this function, and it appears in several ways. But the cool bit is that now you can kind of pass with epsilon to 0. I mean, at least pointwise. And this is what these works by Kohn-Strang and Allaire-Cohn did. They look only at the integrand. And if you do that, you end up with this rho polar of tau. And miraculously, J bar star is rho polar of tau squared over 2. And this is no coincidence, I should say. I mean, there's some sort of convex analysis reason for why they should be related. You can read, there's a section in our paper if you're interested in why they need to be related like that. But the point is, you can also do this for n equal to 3, it gets even messier, and it's even uglier. But again, you can do this epsilon to 0 passage on the level of integrands, not on the level of functionals, but on the level of integrands, and you get some very concrete expression. And again, this relationship here holds. So there is some sort of nice connection. And so what we need to actually do in our paper, so there's some sort of works in the literature that implicitly assume that a certain relaxation theorem exists, but it's not so clear. But if you have F epsilon, which is this Michel integrand, and minus divergence of lambda is roughly F, and H epsilon is this Kohn-Strang integrand, then actually in the gamma convergence sense, this converges to some what's called the Michel functional, which is rho naught of d lambda over lambda. So this is the Radon-Nikodym derivative of lambda by its total variation measure. I'm almost finished. The point here is that actually there are many decompositions of lambda into sigma and mu, and such that this inequality, this relation holds. I mean, you can basically always put a scalar to sigma or to mu, right? I mean, it doesn't care. You can put a scalar to sigma and multiply mu with 1 over that scalar, and you can shift things around because rho has linear growth. This is a linear growth functional. And so what does this mean about our C bar? And maybe the last thing I want to show you, or almost the last thing, is I have a nice example here, which I think makes it a bit clearer. So if you have 2 more minutes, I will explain to you that example. So you just have 2 springs, and they're attached here together, and one is a thick spring and one is a thin spring. And what we will be doing is we will be varying how thick one spring is relative to the other. So we define mu delta is delta on this, I believe is this spring, and 1 minus delta weight on this spring. Then we get an optimal stress sigma delta, and you can check that the divergence of this is some fixed f. So this corresponds to having a prescribed boundary value in this really elementary framework here. And we look at what is lambda delta. And it is, okay, you can just compute this. This is the optimal stress. And what comes out is that the Michel integrand doesn't actually see the delta. It's just constant, and it's actually equal to 2. So the Michel integrand doesn't care. So it supposedly tells you something about optimal mass distribution, but it doesn't actually see if I have mass in that spring or that spring. And that's really not physical because you see, I mean, if you have a fixed boundary F, clearly, what you should be doing is you should be giving equal mass to the 2 springs to get an optimal shape, but this doesn't see it at all. So any delta gives a Michel optimal shape, so it doesn't mean anything. However, if you look at our integrand or the Bouchetier integrand, you actually get something different. And that has the correct minimum at 1/2, meaning that both springs are equal weight. So really, you should say that C bar and not F selects the physically correct minimizer. So the point here is that the point of using the soft constraint, the soft mass constraint, gives you in the limit something unphysical. Okay, so it's just not so useful. You're partially saved by this Bouchetier-Butatsu theorem, which I mentioned, telling you that effectively, if you get a minimizer of the Michel integrand, then you can decompose it in an optimal way into sigma mu, which then minimize the C bar. So there is a connection, but you have to solve an additional minimization problem. And the minimal values are related in a very nice way, right? I don't want to say too much about this, but maybe one thing I want to point out is that what has happened here, I've pulled out the square out of the integral, right? I mean, there's some relationship here where there's a square inside and then there's a square outside. And this acts like some sort of entropy selection criterion on what minimizers have to look like. And then what we can do using this theorem, we can actually construct a recovery sequence, okay? I don't show you the gory details because the point here is to show that, but we use the Lagrange multiplier problem, and then we can construct our sequence. Okay, so I've probably talked already too long, so let me end with 3 open questions, which I think are very interesting. But so the one immediate question is, of course, what can you do for more general integrands J? Well, that's a good question, but we don't know because we don't know anything about the diff quasi-convex hull of those. So this Allaire cone only applies to the simplest integrand. Everything else is a huge mess. And then I'm kind of intrigued by this approximation with these diff quasi-convex quadratic forms. It seems too much of a coincidence that we could construct this. So I don't know if there's a more general principle behind it. And finally, you could ask if there's a full gamma convergence result, but there is some real issues. This might be a significant obstruction. Okay, so I think I stop here. So thank you very much for listening to me, and I'll be happy to answer any questions you may have.
Thank you very much, Phil, for the wonderful talk. Let me begin by opening up to the audience for questions. Steve, did you get your question answered to your satisfaction?
Well, kind of. Beautiful talk, Philip. Very enjoyable. I was actually thinking in slightly different directions. I was wondering about other types of penalization, like surface area type penalizations, other types of energetic structure which could, if you like, select or regularize.
I mean, yeah, so the interesting thing is that all the previous models or all the previous results, as you say, have picked this kind of volume or bulk regularization. Mm-hmm. And but I mean, arguably, we don't. I mean, you pick a regularization according to your intuition on the day. I mean, it's not. I mean, it's not clear what the correct regularization is. Mm-hmm. In fact, it's in some sense it's even worse than that. So let me go back briefly to that slide where I started with the regularization. So here, right? So if you want, there's an implicit constant here. You could also put like a kappa here. I mean, any such thing is a regularization. But it turns out the result really depends on the kappa. I mean, the kappa will be in the final integrand. And how do you choose the kappa? It's like a coupling constant between the penalization and the actual functional you care about. So I don't know. Yeah, I mean, so that was part of the motivation for us to look at the problem with a prescribed size, because there you don't assume any regularization of a particular form. I mean, this is the classical vanishing viscosity problem as well, where you say, okay, add some viscosity, but what kind of viscosity do you add? I don't know actually if people have, I mean, my feeling is, judging from other regularization problems, that if you look at the surface density or things like that, you probably get a very different limit problem, because you are playing into, I mean, a surface density would prevent, or let's say the measure of the boundary would give you a uniform bound on the perimeters, and then in the limit you wouldn't be able to see a diffuse concentration of mass. I guess it depends on what you consider to be a realistic question in your problem.
And maybe if I could, just another, I mean, again, this topology optimization is fascinating.
Yeah.
Are there field theory versions of this, phase field type approaches, which would sort of select the structure by, if you like, an ordering dynamics?
Well, so I guess what we're doing is a field version of this, because we are allowing the field to be, I mean, we're allowing in the limit at least a field of or I mean, a continuously distributed field of mass. I don't know if, I mean, there's various algorithms. It's very much an open field actually for how to compute things. And of course, as you can imagine, these things can be hilariously inefficient to implement, because, I mean, you know, how do you know about starting a hole here? My understanding is that what people actually do in practice is to do some sort of rough topology optimization methods, like where you have a finite number of dots which can be either turned on or off, and then run that thing through some shape optimization to optimize the shape somehow in finite element sense. But I don't think people do this whole thing where you can switch every pixel on or off. I think that's not very efficient. So I don't know. I mean, I don't know if there are any other interesting, I mean, there are lots of ideas in the engineering space. It's a really important problem for them. And I don't think it's been understood theoretically particularly well. Yeah, I mean, I think there isn't, I mean, there's a lot of stuff where I think mathematicians could really contribute to coming up with a good idea of doing it. So what you say is certainly very interesting. It's largely unexplored territory, I would say.
Yeah, fun talk. Loved it. Thanks.
Can I ask you to go back to the lower bound?
Yes.
Yeah, right here. So you have this quadratic functional, and is there? I see that there's a reason that you must go to this slightly more complicated lemma here. Is there a reason that you can't go below by affine functions past the limit and then recover it in the after you've got the limit, then take the supremum?
No, because the problem is you want this to have a sign. I mean, if this has, I mean, we don't know anything about the sign of tau epsilon. I mean, if you have an affine function here, you could shift everything up and down. You can do that, but you will get it on both sides. I mean, we do really need here that you end up with this functional, and here we end up with something that has an asymptotic sign. So, I mean, this has not got us, I mean, this doesn't have a, I mean, this is positive for tau epsilon, I mean, for epsilon greater than 0, but in the limit, it could also be negative, but in the limit, it disappears. So, I mean, the point is that you need to find a sufficiently rich family to approximate the J bar star, and then use that family to shift up and down and kind of show that something that you have shifted up. So, I mean, this shifts it down, this shifts it up, but the point is that this in the limit is actually is 0. So, I mean, you can find larger families, but they don't really accomplish what you want. I mean, I think if you shift,
I'm thinking about the question that you ask about for more general integrands, and so of course this is an argument which works because of the invoking of this this precise theorem, and I just wonder if you don't have this theorem, then how do you get around into more general cases?
So the Tartar compensated compactness theorem holds also for any differential operator, and for any quadratic form that is A quasi-convex with respect to this differential operator A. So this is the same. So that you could do. The difficulty is for general A, can you construct such a family? I mean, it's more that this is by hand, okay? So I mean, this is quite literally we spent, I don't know, a long time guessing what the function what they would look like, inspired by this previous paper in fracture mechanics where we had something similar in an, if you want, easier case. And then we just guessed it, and then at some point we could establish it.
This back right here. What that says is, can you go back one more slide?
Yeah.
I'm sorry. So because the Q has the 1/2 tau squared and the J star bar has the 1/2 tau squared, what you're saying is that if you take these 1/2 psi dotted with inner product with tau, where psi is over a very precise family, then you can get it. And so I guess that's the question about whether the general thing can be recovered as these supremum.
So you mean for more general integrants?
So if you have some integrand, then how do you view it as the supremum over these inner products?
I don't know.
Yeah, that's the.
I mean, it's not clear at all, actually. I should say that in the other paper, the previous paper, we do get a family for a kind of similar technique, and it applies to more general integrants as well. So my feeling is that if you spend a lot of energy trying to construct things here with linear algebra, you can probably go beyond this integrand. I mean, for instance, I mean, the next question would be, can you at least do something like this, right? Tau squared minus kappa of trace of XOR squared. So the classical integrand with Lamé coefficients, right? Mm-hmm. I mean, and in principle, it should be, I'm not too stressed about this lemma for that integrand. I think, okay, we haven't done it, but I could kind of see this working. The issue is that even for the upper bound, we need this very explicit computation also of Alea cone and cone strang. And that really is only available explicitly for this. I mean, so I mentioned this on the title of the slide, but didn't say it. So this is part of a more general way to compute lower bounds on the diff quasi-convex envelope, which is called the Hushin-Strickman bounds. And this is very well known in this shape optimization community, this Alea book, which is called Shape Optimization by the Homogenization Method, goes into some detail of how you can do this. The problem is that for more general integrands, it is very implicit. It's basically you saying, oh, there is a bound, which is very implicitly defined by some other optimization problem. And that bound is a lower bound on the diff quasi-convex envelope, but it's not clear it is the diff quasi-convex envelope, it's just a lower bound. And so everything is a lot less explicit. And so we don't have the upper bound for that one either. So, I mean, basically for to go beyond those very simple integrants, it needs a lot more work. I think it's an interesting problem because my feeling is that there is some sort of general principle here that one can understand and that will give you some insight into similar problems as well. But it is certainly significant extra work. So I think this lemma could probably be generalized. But even then, it's not totally trivial. If you look at the proof, I mean, you have to do a few things which took us a while to figure out.
So maybe we have time for one more question from Steve.
Yeah, I'm getting excited about these problems. They're very interesting. So what about other geometries? So, I mean, in some sense, you could say, okay, just in the abstract, you could stick this in a sort of a Riemannian geometry sense. But I was thinking about a sort of particular sort of idea, which would be, suppose you actually a priori wanted thin structures. So you sort of have the idea of, I'm looking for, let's say, effectively a membrane, but I want to know the microstructure within the membrane. This is sort of codimensionally lower and touching on the Riemannian. have you thought about problems in that direction?
Yeah, that's a beautiful question. Okay, so the one problem you have like Kossara vectors and issues with this, of course, because you have some intrinsic curvature in that thing in the ambient space.
Yeah.
I mean, my honest feeling is that this is a very great problem, but our analysis of those
Sure,
problems
but it
isn't quite there.
it could be fun.
But
It could be fun to get into.
so what, yeah, and actually, so there is maybe this is actually, so there's something really cool that I read about. There's an article, I think in Nature, where people talk about this printing of shapes, and what they do is exactly what you described. So they have like a drip in the middle, and they kind of manage to impose certain microstructure in the material at the point where it's kind of created, and then it goes outwards and it forms a complicated shape, which is kind of programmed by how you precise put the microstructure.
I've seen that. That's this pre-programmed metric.
Yeah, it's really interesting, and
yeah.
I think that would be a fantastic question to investigate. I have to say that it adds another layer of complexity, because you now have to do everything in manifolds where, I mean, even some classical notions are not so clear. I mean, so for instance, it's not even that clear how you want to do measure theory on manifolds in general, right? I mean, and everything that is in geometric measure theory is, or most of what's in geometric measure theory is really on an embedded manifold. But then it's not, it doesn't strike me as being impossible. It just strikes me as being very complicated. But if we have another pandemic, if we have wave 3 and 4, maybe that's what I need to spend my time on doing.
Plenty of time. Fantastic talk, Philip. Thanks.
Thank you. Thank you.
Yeah, so thank you again, Philip. Let's, well.
Thank you.
We'll stop the recording here.